Hello and welcome to week 13 of Introduction to Meteorology at the American Military University. I hope you're having a great week, and I apologize for getting the schedule mixed up. So week 13 in the book, chapter 13, is about the changing climate, and the textbook goes into kind of how do we measure climate, both in what we call the instrumental record, and how do we go back and infer or estimate or calculate conditions before we had thermometers and rain gauges around the globe. So that's the start of the chapter, and then we go through some historical climate stuff, and then some drivers of climate change and consequences of climate change and feedback mechanisms within climate change, and that's pretty much where we're going. So this material and the week before it, both the kind of the climate, not considering climate change, and then the changing climate, that is where I professionally kind of spend my time now. I'm an old meteorologist that kind of accidentally got into climate stuff. So the changing climate. Here's how the chapter's laid out, and what I'll go through is, first of all, kind of a preamble to the chapter. He mentions that the climate is always changing and always has changed and will be expected to change in the future, and that's absolutely right. It's a dynamic system. The temperature and the way water moves around in the climate system and all of the kind of interconnected processes are dynamic, both internally within the climate system and in response to external drivers. And he kind of gets in a little bit on what externally can drive the climate system. But to just kind of sequence through the chapter, he first goes into reconstructing past climates. So how do we know about time, kind of what in climate, kind of the prehistorical times, or the pre-instrumental is what we call it, times, which is kind of mid to late 19th century, when we started to have enough measuring devices out there, thermometers, rain gauges, to get a picture of kind of what the Earth's temperature and is. So before then, we have to kind of reconstruct the past history, and he has some great examples, some really cool kind of CSI stuff that those guys do when they're reconstructing past climates. He's talking about sediment and pollen and ice cores, and even tree rings, for kind of that last 100 to a few hundred years. And the thing that kind of all of these methods have in common, they all kind of look for different things, and some of them are a little more about chemistry, and some of them are a little more about tree growth. But what they all do is they compare some layering. So all of these things, whether it's drilling into a tree from the most recent time to the middle of the tree when the tree was born, or if it's drilling an ice core or looking at sludge from the bottom of the ocean, all of these kind of measures have a seasonal or an annual layer that's laid on top of the next, or in a tree's case, kind of built on around it as the tree goes. And reconstructing the past climates has everything to do with very carefully kind of deconstructing this big, giant, layered puzzle. And they have some amazing methods and really smart and people that are figuring out what went on in past climates. So he kind of goes through some examples, but the punchline of that entire section is evidence is laid down in layers, and these scientists go through and kind of unpack those layers and kind of go backward in time from the most recent to the most distant in time. And that's how they build a history, an understanding of the historical climate. Okay, so after kind of how do we build the prehistoric or pre-instrumental record, he goes into basically walking through the kind of known climate history of the Earth from millions of years ago till today. And he zooms in on kind of the last millennium, last 1,000 years or so, and this is figure 13.5 is the famous hockey stick graph. It shows how this century is warmed, unlike any of the centuries immediately before it. Then he kind of zooms in to the past 130-ish years or so, which is the instrumental record, meaning this is when we had enough thermometers around, or weather kind of temperature observing stations around the world, and enough reports from ships at sea to get ocean and land temperatures to get some kind of global estimated value. And then very recently, satellites have been added to that instrumental piece as well. We still rely on weather stations just like we did in the late 1800s, and we still rely on ships at sea and buoys to give us temperature information over the oceans. The oceans take up more than half of the planet, and good observations over the ocean are an important part of getting an accurate temperature for the planet. So we still rely on those things, and the addition of satellites has really helped us fill in the gaps in those records, but we really rely on the long-term history of that station and ship and buoy data. Then he gets into after we walk through kind of the history of the climate system and when we were warm and when we were cool and what have the changes been, he starts talking about processes, and he talks about natural climate change, and he breaks it down into three forcings or drivers, or what he calls external causes of climate change. And one is changes in the amount of sunlight or solar radiation that the Earth system receives, and that can be due to fluctuations in the sun itself, putting out more or less energy, and that can also be due to cycles in the Earth's orbit as well. And then talks about changes in the composition of the atmosphere, and this has to do with gases and particles and just basically the stuff in the atmosphere. As the relative percentages of different greenhouse gases increase or decrease, that can have a warming or cooling effect on the surface of the Earth. And as you introduce more particles into the atmosphere, tiny particles, and the natural process that does this is volcanoes, you can kind of cause a dimming effect where more of the sunlight is captured high in the atmosphere before it reaches the ground, tends to cool the lower part of the atmosphere. And then changes in the Earth's surface, and this is kind of where he introduces feedback mechanisms. And so kind of the two classic positive feedback mechanisms, and he spends some time here, is the second one is actually the more kind of easily grasped, or the one that's a little more familiar, and that's he calls it snow albedo feedback. But basically, snow and ice cover on the planet, as that retreats, as snow and ice retreat, as the world warms, snow and ice retreats, it exposes more ground or water that used to be covered by snow and ice. So instead of being a really bright reflective surface that reflects a lot of the sun's energy, as that retreats, it exposes a darker surface, whether it's water or land, which absorbs more of the sun's energy, which causes that place to warm relative to when it was snow and ice covered, which kind of feeds into the process, kind of amplifies or accelerates the initial warming. So that's an example of positive feedback, and he talks about how in a warming world you're going to evaporate more water into the atmosphere, and water vapor is also a greenhouse gas. So a warmer atmosphere likely has more water vapor in it. Water vapor is a greenhouse gas, which tends to accelerate the warming even more. So he gets into positive feedbacks as well. A little later in the chapter, and this is good stuff to pay attention to, some natural drivers of kind of longer-term climate changes or variability are the Milankovitch factors, and these are basically three aspects of the kind of physics of our orbital dynamics around the sun. And they are eccentricity, or how circular or oblong the orbit is, and that actually goes through kind of a cycle, trying to get from very circular to a more eccentric orbit, and this varies over the course of a few tens of thousands of years. Precession, which is like the wobble of where the North Pole points over time, and that varies over a couple of tens of thousands of years. And then obliquity, which is tilt, which is at times our poles will be pointed more kind of to and away from the sun, and at times our poles will be really, really upright as we orbit the sun. And as you tilt down, where your poles are pointing more toward and away from the sun, that can cause like more intense seasons, which can launch ice cycles. And these factors together, and they don't happen on the same time scales. They're all kind of vary over several tens of thousands of years. But the kind of interplay between these factors have driven a lot of the big changes that we've seen in the past. These can kind of launch these positive feedback things, where if all of those factors are kind of lined up to be a cooler world, well then the ice sheets start to expand, which reflects more sunlight, which is a positive feedback, which cools off the surface a little more, and so on. And so these are important factors in the natural climate history of the Earth. Then he gets into particulate matter, and basically the punchline of that is that volcanoes can inject a lot of what we call aerosols, or small, tiny particles, high into the atmosphere, into the stratosphere, where they kind of live a long time, months and years. And we've had three big volcanoes, three really consequential volcanoes in the last 50 or 60 years or so, and those have led to months and years of relatively cool periods after them as well. So the name, he'll give the names and examples in there. So after the natural factors, he goes into the anthropogenic or human-caused climate change, and again, aerosols. There's a natural component with volcanoes, but aerosols, as they get into the atmosphere, they can regionally, in some cases globally, kind of cause a dimming effect, which can cool things down. They can also cause the acidity of precipitation to change, depending on what those particles are. He talks about that. And then he talks about increasing greenhouse gases, and he does mention, doesn't go in a lot of detail, it's not just carbon dioxide that's a greenhouse gas. Water vapor is a greenhouse gas, methane, nitrous oxide, and then some more exotic gases called CFCs, and there's a whole family of gases. And a lot of these are pound for pound a lot more potent than carbon dioxide. And so, if these are more potent pound for pound, they actually are more greenhousey. They can trap more heat per pound than carbon dioxide does. The reason that carbon dioxide is kind of the greenhouse gas, with kind of over and above these, is because there's a lot more of it. There's a lot more carbon dioxide, and it's also a very stable gas. It can last for hundreds of years in the atmosphere. So once carbon dioxide is released in the atmosphere, there's kind of chemically it's fine, it likes the way it is. It doesn't react with a lot, so it doesn't really break down. So it can last hundreds of years in the atmosphere, and so that's the combination of that. There's relatively more carbon dioxide than these other gases, with the exception of water vapor, and the fact that it lasts a long time is the reason it's kind of the greenhouse gas. Methane is increasing in its importance, and it's a pretty potent greenhouse gas, but it doesn't have near the concentrations yet that we see in carbon dioxide. The reason water vapor isn't really, it doesn't last very long in the atmosphere. It turns into precipitation eventually. It turns into cloud particles or something. It does have an effect in that if the average amount of water vapor in the atmosphere is going up, then this water vapor is also contributing to warming as well. And then he talks about land use changes, and this is kind of the changing the shape or reflectivity of the land, whether it makes it more or less reflective, or removing trees and turning land into agriculture. Well, that can have an effect on both like the albedo and the plant life that grows there as well. And then he talks about, he kind of goes into is this warming that we've seen in the last 100 years, how do we know it's due to human activity and not just some natural cycle? And he goes through kind of, step by step, the typical stuff that you'll see. The first reason is kind of, we know that carbon dioxide and these other gases and greenhouse and water vapor trap heat, and that's kind of they're physically known to do that. So they would be even if we weren't observing this, we would be expecting them to contribute to heating. He talks about climate models and how they, basically, to the best of our understanding now, when we turn off the humans in the climate models, which means when we keep the greenhouse gas levels at a kind of natural state, we can't reproduce the warming that we've seen. When we turn on the humans in the models, it does reproduce the warming that we've seen this century. And so the combination of kind of this chemistry and physics knowledge and to the best of what we know about the climate system, and we model it, and it can reconstruct what happens when we include the humans, together, that tells it's pretty obvious to science anyway that greenhouse gases are driving much of the warming that we've seen. And he talks about the state of the climate in 2009, which is, I haven't seen this my first time. The reason I kind of screwed up the weeks is this is a new edition of this book. I was actually the editor of the State of the Climate in 2009, so it was kind of neat to see a lot of people's hard work make it into a meteorology textbook. And then he talks about future climate change and the kind of scenario-based, if we burn a lot of fossil fuels, we'll accelerate the warming by this much, and so on. And then uncertainties, and that's a big topic in climate, and something that we've kind of constantly not done a great job of, honestly, as professionals, is understanding and especially communicating the uncertainty in what we do. This is all pretty delicate stuff, and we're talking about hundredths and tenths of degrees, and anytime you're trying to do something that precise, you should do a better job of kind of saying, well, the best estimate is right here, but there's a margin, a window, it could a range of uncertainty. And so he talks about kind of on a gas by gas basis, the uncertainty involved both in the concentrations and in their role in increasing the radiative forcing as well. And then he gets into the question of clouds, which I think I alluded to just a minute ago, on whether that's a positive or a negative feedback. If you introduce, if a warming world evaporates more water and causes more clouds, are those clouds going to be more reflective and be a negative feedback? And there is some back and forth in science on that, and there's been a lot made of that, the kind of uncertainty in that. And the truth is, they'll figure it out. There's a lot of good research going on. The fact that we are understanding the climate system in the big picture anyway, as well as we are, tells me that whatever we figure out on cloud feedbacks or cloud processes is just a little smaller in scale than these other larger feedbacks. And then he gets into the consequences of stuff, of climate change, and I don't think we're testing on that. He does talk about sea ice retreat. That might be worth knowing. That's a physical thing. And then he talks about the kind of what do we do about it, which is the theory, or not the theory, but the kind of proposed solutions to climate change involve either just dealing with it, kind of accepting it and dealing with it, or mitigation is the other thing, which is like actively trying to reduce the amount of greenhouse gases that are produced and put in the atmosphere. And then the other thing he mentions is geoengineering, which means try to do other stuff to kind of counterbalance the impacts of climate change. And that's pretty much it. I don't think we'll have many questions on, what do we do about it? That's not what this class is really about. But it is a big issue out there. It's on a lot of people's tongues and minds, and it's probably not going away. So that's the chapter on climate change. The punchline is it's changing. It is a dynamic system. It has always been changing. To the best of our knowledge, the changes in the last century are primarily driven by greenhouse gas warming. the temperatures, the global temperatures anyway, that we have seen, to the best of our knowledge, are explained by increases in greenhouse gases. The detail, no one was ever found dead under a trace of global temperature. So the challenge in science is, what does, we know that the planet is warming. It's, what are the local and regional consequences of that? How is that going to play out, both in temperature patterns? How's it going to affect circulation or precipitation patterns? Those are the important questions that are still there. And you mentioned uncertainty. There's a lot of uncertainty in how this is exactly going to play out. We're pretty doggone confident that the planet, the entire planetary system, is going to heat in proportion to the greenhouse gas increases. How that plays out on the surface, who are the winners and losers in that scenario? There's a lot of science left to be done on that. And by winners and losers, I mean, how is the weather or the climate of places going to change? So that's a challenge. We've got a long way to go on that, and there's a lot of exciting research to do. All right, that's it for the climate change chapter. I hope you have a great week. Please email me or send me a message, or on the forum if you need some understanding about late assignments. I've kind of not done a great job the last couple of weeks. I'm staying on top of where we are. So if you're in that same situation, if you've got family stuff or work stuff or military stuff that's that you need some understanding about, let me know, and we'll work it out. Other than that, please stay safe and have a good week. And this world is better off because you're in it. All right, bye-bye.